Welcome to today's podcast. In today's session, we have with us an expert from a field related to batteries. Ramesh Natarajan, a veteran with over 42 years of hands-on battery industry experience, will be asking our esteemed guest a host of technical questions. Hope you find this podcast useful to your business. Enjoy the session. Do visit www.rameshnatarajan.in to stay connected.
Welcome, dear listeners, and thanks for tuning into this episode of my podcast. Today, I have a dear friend, Mr. Achim, to discuss an important aspect of battery manufacturing. Your response to the previous two episodes featuring Mr. Achim has been fantastic, and I'm sure you'll benefit from listening to him today as well. In a previous episode, I highlighted the importance of battery charging. That was in April 2023. The episode was Secret Revealed, the Key to Long-Lasting Batteries. However, we have both realized that battery formation still doesn't receive the attention it deserves from the battery manufacturers. Many high-quality batteries perform poorly in the field or have a shortened lifespan due to neglect during the final stage, that is, during the battery commissioning charge or initial charge stage. Mr. Achim and I believe this critical aspect of battery manufacturing needs more focus and proper resources. Mr. Achim has served as the CTO, that is the Chief Technical Officer of Hammond Industries, and he has also been the R&D Chief of Excite India. Now he is doing consultancy. He's a busy international consultant, constantly traveling and often away from his base in the USA, and keeps postponing all the schedules of the podcast that I decide with him. I love doing podcasts with him, but securing his time is not easy. Mr. Achim has over 34 years of extensive experience in this field of battery manufacture. I greatly admire his willingness to share his knowledge of lead-acid batteries. Mr. Achim, our regular listeners are well acquainted with you, but I would still appreciate if you could give me a brief introduction about yourself before we start our session, for the sake of the listeners.
My pleasure, Ramesh. As you know, it's always an honor for me to do a podcast with you, and I'm excited to be here. I believe it's now the third time, right?
Yes, it's the third time you're doing it.
Mm-hmm. I think you've said it nicely. As far as my background is concerned, maybe for the listeners, it might be interesting where I'm coming from. You know, I'm by trade, I'm a physicist. And at the end of my graduate studies, I wanted to do something real cool. And the last thing I wanted to do is go into the lead acid battery industry because I thought it was rather boring. And all my friends did something really cool, nuclear physics or something. But I had to make some money. And there was a industry cooperation project with Data batteries, which is in Germany, which is now Excite technology. So I had the chance to work for them. And then it has been ever since then a fantastic ride. And what might be interesting also in terms of formation, what we're talking about today, my first ever assigned job in the industry was to develop formation profiles for gel traction batteries. So from the very first moment, I got involved with formation.
Yeah, and Mr. Achim, I think it happens to everybody, though we think that batteries are probably boring and there's a lot of acid and lead and everything, but people who get in, you know, there's some magnetic pull sort of. Many people in the industry are people who have spent 12 years, 15 years, 20 years, 30 years, and they retire from the industry. They don't generally change from the battery industry to something else. I don't know what's it that attracts them and keeps them in, you know. So I have a lot of people whom I know, they are all in the battery industry for years, like. And it's an interesting subject anyway.
Absolutely. It has become my passion, actually.
Yes, that's very nice. Okay, now, to start with my queries for today's episode, I remember during a previous conversation, You mentioned that, I mean, most of the times where you do your consultancy work, you specially focus on the formation process. Now, why is it so? Like, why do you do more focus on the formation in many of the factories that you visit and you offer your consultancy and you work with? Why
You know,
so?
yeah, good question. So actually, I've gone so far as to usually when I visit a new factory, a new customer for the first time, I do the process audit or process review in reverse. I really
Hmm,
start with formation, and then
hmm,
after that, I work my way backwards.
hmm,
And usually it's like what I would call low-hanging fruit, because in formation, you always find something. And to
hmm,
me, it's like amazing that a lot of very, very sophisticated, thinking has gone into the paste making and
hmm,
curing and everything
hmm,
else. But formation, there's often an understanding that all you need to do is to apply some current over a
hmm,
certain period of time, X times the ampere hours or something like this, and then it's done. And the only really concern that we mostly have is high temperatures. So there is people are very concerned with temperature, sometimes actually too much, but they are hardly ever concerned with overcharging the batteries.
hmm, hmm,
So in most cases where I go into companies, I find excessive overcharging of the
hmm,
batteries or the plates, which then, of course, in the end impacts the performance. You can do everything right in the very beginning, but then
hmm,
you can, jokingly speaking, mess it up all
hmm.
at the end. So that's why I find it's advantageous starting at the back and then going forward.
Yeah, I mean, people make a good battery with the best of intentions and then finally spoil it and give it to the customer.
Yeah, unfortunately, that's what happens quite a bit.
Yes. And I mean, you said formation. So for those who are not so familiar with this, the technical word, so to say, can you explain what exactly is formation and what are the steps like in formation?
Mhm. Very simply put,
Hmm,
formation is the first charging of
hmm,
the active material. It's
hmm,
actually the activation or the forming of the
hmm,
active material out of the cured and unformed plate. So that's where the word formation really comes from.
hmm,
And it's actually very similar if you look at the chemical equation of charging and you compare it to any other charging in the later life of the battery, but it's fundamentally really very different, because if you think about it, formation means the plates that you have there that you are to be formed, they come out of curing. So they're basically a mix of basic sulfates and lead oxide.
hmm,
And then if you compare that to any other charging that happens later, it's basically an electrically active electrode, PbO2 in the positive and Pb in the negative, that has been partially discharged, and that then you have to recharge. So I always, I really don't like to use the term charging to
hmm,
describe this process, because for me, formation, the activating of the material of the paste, making it electrically active, and the recharging after discharge are really two different things. And I would like to
hmm.
distinguish and separate between the
Yeah.
two.
See, that's why even I talked of initial charging and commissioning charge. So we also, factory, when we do the green plate, we call it a initial charging because it takes a much longer time. But suppose we are already using a formed plate, jar form, I mean the tank form plates, which are already, charged from the unformed state, and then
Mhm.
doing it, we call it a commissioning charge because then it becomes very easy. Initial charge is for a longer period, and they are with plates which are, only cured, and commissioning charge is for a much shorter period, and they are for plates which are already formed. So
Mhm.
that is how we also differentiate in our
Yeah.
factory generally. So initial
Very good.
charging and commissioning charge. Okay,
Mhm.
now what types of formation are there and what are the differences?
Okay, so the answer to this could be either 5 minutes or could be 5 hours, I think. But let's try to keep it as short as possible and as, I hope, informative as possible. So fundamentally, there are two different ways
Hmm,
of doing formation. There is
hmm,
the tank formation
hmm,
principle, and there is the jar or container formation.
Yes.
In the tank formation, we basically still have the individual plates, usually double plates, that we put sideways in a huge tank filled with highly diluted acid. And then we basically connect all the positive plates because they're resting on a positive lead bar. And then we have the other one, the negatives, that connect, the lugs all connect to the negative bar. They're on the bottom. So that's the easiest way of doing it. And then basically you apply the charge and you charge the plates individually, I would say.
The tank formation.
A good friend of mine once said in the very beginning when I started in the industry and I learned about all these things, he said, this is going to go away one day because, it's basically you build the battery twice. Because basically you have an extra step you build basically a 2-volt cell, which is the individual's tank. Later you have to take them out manually, and do all that kind of stuff. So what has become more popular is the jar and container formation. It's more economically viable. You basically already build the battery, assemble it with the cured, not active yet, plates, and then you fill the battery with a also diluted acid, not as highly diluted. It's a little bit of a higher gravity. And then basically you connect batteries in a circuit together and you apply the electrical current, the formation current, and then you run a certain profile, and then you form the battery accordingly. And then there is a subset to that. That is, there's a difference between a one-shot and a two-shot formation. Most people today use the one-shot formation, which means you fill it once, you fill it in a way, and you choose the gravity in a way that you come up close to the nominal gravity, and then you top off, and then you're done. The two-shot formation, you use a very highly diluted acid, closely to what you use in the tank formation. You charge the batteries. Charging efficiency is much higher with the low acid gravity. But then, of course, afterwards, you never reach the nominal acid gravity. So you have to dump out the batteries and you have to refill them. And so there's an extra step, which then again has some, environmental impact and things like that. And then the last one that I would mention in terms of jar formation is the electrolyte circulation systems that have became quite popular, I think, over a little bit of 10, 15 years ago, where you want to really charge as fast and efficiently as possible. That's why you use cooling of electrolyte by pumping and circulating the acid through the batteries as they are charging, and then basically run them through a cooling tower and refill them with a lower temperature electrolyte. That way you can keep the battery temperature in check very well. You have a very short time, but of course the system also has its problems, and we might get into this a little bit later. So all the different systems, they are for a certain purpose and application, and they have advantages and disadvantages.
Now, we talked of one-shot formation, two-shot formation. We've talked of jar forming and tank forming. Which type is your favorite and why?
Okay. Oh, it's a very good question. It's a little bit of a tricky question.
You'll say tank formation, but then it's messy.
I would just answer diplomatically that it really, really depends on the application and economics, right? So, for example, the tank formation has a lot of advantages. I think it is actually probably the best formation that you can do, because there's two advantages to it. Number one, you fill it with an extremely low specific gravity, which is 1.05 to 1.15. People use, the whole range. And what that means is you have a very, very effective formation, very good conversion, particularly into PbO2 in the positive active material. Another advantage is that because those slots that I talked about, where you put the plates in, you can choose if you put one or two or several positive and negative plates in. That means you can balance the amount of active material in the tank in a way that you never overcharge one or the other. So you have a very balanced formation. So if you go from a quality perspective of the plates, this is really a very, very good a system. The downside is the additional process steps. And then once you take the plates out, you have to make sure that particularly the negative plate is protected, because this fresh metallic lead surface of the negative electrode has a propensity to oxidize immediately. So you have to have another process step, either vacuum drying or dunking it into boric acid or something that protects the negative plate from oxidizing. So good quality, definitely not the most economic. So my favorite, as you asked, is the one-shot container formation, because I believe it's the best compromise of all of them. Economically, you build the battery only one time, so to speak. And, if you manage your profile very well, the way you apply the electrical current, the way you choose your filling gravity, I think you can have a plate quality similar to that of tank formation. The double shot has come a little bit out of fashion because, as I said earlier, you have the dumping process. And so there is a little bit of a safety issue to it. You have to neutralize the acid that you dump out. You have to collect it correctly. And another issue is, but one of the upsides of it is that you can use a very low filling gravity, almost close to tank formation, which then again gives you very good formation efficiency. So you can make it shorter, except the additional process step. The acid circulation system, and here I'm talking a little bit more about my own, well, I would say gut feel about it, without ever having done really a scientific study is. A plate naturally, if you apply a constant voltage, a plate or a cell naturally draws a certain current. So that's what the plate is, let's say, comfortable with. Even if you keep the temperature down and you cool in an electrolyte circulation system, you cool the acid, but you force tremendous amounts of current into the battery. The battery, I think you cannot really rush the natural chemical reaction. So I think that there is some kind of downside that will result in a somewhat diminished quality of the plate. The upside, of course, is you will have extremely short formation times. Another downside is, you may have watched this over the past few years, there have been quite a few fires and explosions in battery companies surrounding electrolyte circulation systems. I've actually worked at 2 companies, and in each of those companies, we had electrolyte circulation systems that caused a great fire. And that is due to the fact that you use extremely high currents together with a high voltage. That's a lot of electrical energy. And then, of course, you have an explosive mix, a flammable mix of oxygen and hydrogen, which may then, under the wrong conditions, lead to exactly that. But so all of this given, and coming back to your initial question, the one-shot formation to me is the most effective compromise of all of them.
Another advantage, like to add to this, in the tank formation, we have a lot of electrolytes. So the temperatures don't go up in a tank formation, which is another advantage. But in the case of one-shot formation, the temperatures can go up, and we may have to keep it in water bath or something like that to keep the temperature down, isn't it?
That is correct, yeah.
Yeah. And if we focus on jar formation for a moment, because you say one-shot formation, and it's not only that you say, I've seen that a lot of people prefer that only, the one-shot formation. So when that is the most commonly used and the most popular method of formation resorted to nowadays by the battery industry, can you walk us through the basic steps and tell us what needs to be carefully done, or what we have to watch out for? Because that, for the listeners, would be something which will be very enlightening, and probably if they are missing out something, then it will be helpful for them, and they'll be able to take care of what not to do and what you have to watch out for.
And I think a big part of this answer is actually the initial statement that you made, that it is a compromise, right? So one has to understand, and this is, I think, is the core of all design of formation profiles and systems, is to understand that the positive and the negative plate, they actually need naturally a different treatment. If you look at the theoretical calculation you get from the mass formula and the Faraday constant, you find that both the negative and the positive plate to be activated need about 220 ampere hours per kilogram each, right? So that would give you naturally how much electricity you need to form the batteries. But the reality is different because they behave differently. When you charge them, when you start the formation, the negative plate accepts all the electrical current immediately. And once it reaches those 220 ampere hours per kilogram, it shuts down and absolutely accepts nothing. That means it will have very vigorous gassing at that point in time, evolution of hydrogen. The positive, however, starts at a little bit of lower level of charge acceptance. And when the negative is full, it still needs significantly more charging. So while the theoretical for both is the same, the negative really shuts down at 220 ampere hours per kilogram is fully charged. The positive needs at least 340, 360 to be fully charged. So inherently, in any formation, you have the problem of overcharging the negative. And that is really the key here to understand. The tank formation, as we said earlier, by putting more negative plates into the slot, you can level that, and you can make sure that with the same amount of ampere hours that you put in, both plates get exactly what you need. But that's why any time of one-shot, two-shot formation is a compromise, because you have to manage the fact that you always overcharge the negative plate. So now coming to the steps that you mentioned. So now if we fill the battery, we usually start with diluted acid. And in a one-shot or a formation, what you do is you choose the acid as low as possible so that during formation, when the acid comes up, you will at the end be close to the nominal acid gravity that you would like to have in the battery. So usually people choose somewhere between 1.2 to 1.20 to 1.23 grams per cubic centimeter acid gravity. So after the filling, the magic actually starts, right? Because then you have to use your time current formation profile. You turn on the current, and you need to do this in a certain way that actually helps the plates to charge correctly and at the same time manage, as we talked about, this difference between the need of the positive and negative plate. So you start with a very low current for a little while. And you should start a little bit earlier. Once you've filled with the acid, there is a so-called soaking period. The soaking period, basically what happens is the basic sulfates and the PBO, they start to convert into lead sulfate on the surface. So when you turn on the current, basically you have an insulator that the current is facing. You have the inactive bulk of the material, and you have the sulfate. So you slowly now, with a small current, have to convert that lead sulfate into PbO2 in the positive, Pb in the negative, and through that conductive path, basically pump further current in and totally form the plates. So once you have enough conductive material, you can actually, in a second step, raise the current. And this is the step that is the most efficient formation. Both plates almost accept everything that you're offering them at that state. So you don't have to watch very much the temperature in this state. You can go sometimes as high as your rectifier allows to get the most efficient formation and save as much time as you can. As soon as the negative plate is full, then what happens is the voltage jumps up, the gassing starts, and actually the overcharging of the negative plate starts. At that point, you need to drastically lower the current and then continue until you have enough ampere hours in to have the positive also fully charged.
Mm-hmm.
So no matter how you exactly do it, people have very sophisticated profiles with pulsing and with pauses, and but you have to keep in mind those three basic steps. The very low current in the beginning to create a conductive path, the main formation phase where you can pump in as much as you can, and then the full hitting the brakes and going down with the current to protect the negative active material during the time that the positive still needs to be fully formed.
So when you say as much as the rectifier can pump, the rectifier may have a very, very high capacity. So, I mean, we'll have to give some percentage which relates to the battery edge capacity.
I'll give you an example.
Yes.
When I started designing formation profiles, the question that I asked myself was, or we as a team asked ourselves was, how do I know what the plate wants? So what we did is we put certain 2-volt cells and we put a high voltage on it, something like 2.67, 2.7 volts. And then we let the current run free and just see what does it do. And basically what it does in the beginning, a very low current, right? Because you have a high resistance. Then it basically runs all the way up, sometimes even for a small starter battery, it would be able to accept 30, 40 higher amps during that period. And then it drastically, when the negative gets full and you maintain the voltage, it would drop down, right? And then it would go almost to zero to cautiously form the positive plate. So that is something that you can't do in real life because you want to keep formation short. But if you mimic those steps, our philosophy was, then you have the ideal formation profile. And we were so surprised to see how much current the plates would actually draw if you let them. So I would say if you have a rectifier, usually formation rectifiers are 25 amps or something like this, maybe 30 max. But you can use that in that second phase without any concern.
Yeah, I understand. But what I mean to say is, suppose it's a 32 ampere hour battery, automotive battery. Do you think we can put 30 amps? Or would you like to restrict to 15 to 20% of the capacity?
I would actually see, and I may be at odds with some of the people that are listening, but I think that's a good thing, right? To open this for discussion, right? But in my experience, you can really go very high because and there's another thing that might be shocking you, but the temperature during that phase is truly not of much of a concern. The temperature becomes, and we always, we think like we need to balance the temperature, never to go above 55 degrees Celsius and stuff. But it's really not true. The damage starts once again when the negative plate is full. That's where you have to start to really very adamantly control the temperature. In the earlier stage, is not actually needed, and therefore you can actually go quite high even on a small battery.
See, that is probably the thing when you come to pasted plate batteries. But when you come to a tubular battery, above 55, the tubular bag starts getting affected, the bottom bar, which is a plastic component. So that's why
I'm talking
for pasted plate.
Correct. I'm really talking mainly automotive and
automotive. So now, suppose it comes to tubular, then probably we got to restrict it to 15 to 20% of because there the temperature will matter for sure.
I do not disagree. Yes.
Yeah.
Yes.
Okay. Now, because we talked of temperature, so coming back to why is temperature control so important during formation? Because it is important. So, of course, I have mentioned about the tubular, but I mean, I would like to hear your views, whether you have some other.
As I, mentioned before, what I mainly see, everybody you talk to when you come, when I do my consultancy work, everybody said, okay, so what we're doing is we have a great focus on temperature control, right? We control the water bath temperature, the flux, all kinds of things. Some people even use cooled acid, right?
Chilled acid, yeah.
Chilled acid for filling. But then again, but then they don't. The same company then has no problem, overcharging the negative like maybe twice as much, as it needs. So I would like to, when we talk about temperature control, the temperature control once again is the most important during the second phase or the third phase of formation when the negative plate is full. Because what happens is, and this is also some we did. I don't know how many years ago, almost 20 years ago or something. We actually looked at, there was a common understanding and an observation that when you tested batteries that went through a very hot formation, that they would not perform well in their cold cranks or any type of high rate discharge, and they would also not do very well in cycle life. So the question is, where does this come from? And so we looked at the different components, knowing that the negative plate is full very early on during the formation.
Yes.
And we found that the temperature alone doesn't really affect it, but it has an effect if you have at the same time temperature and an overcharge potential, which would both come together exactly at the point, from the point on when the negative is full. And when we investigated further, we found that actually the organic complex of the lignosulfonate that is part of the expander in the negative plate actually decomposes or explodes, so to speak, if you induce energy into the complex based on thermal energy through the heat and overcharge potential, which is basically electrical energy. So when those two come together, you will damage the negative plate and its performance, and cold crank, high rate discharge, cycle life will diminish, because that's the job that the lignosulfonate basically does in the negative active material. So you cannot prevent the overcharge potential only by reducing the current. You can do a little bit about it, but at that stage you can actually lower keep the temperature low so that you minimize the damage that you're doing to the negative plate.
Yeah, and this concept of chilled acid being used, I mean, though I'm digressing a bit, it's more, it became more popular after the advent of the VRLA batteries, and where they didn't want the high temperatures. And then people started using it also for the flooded electrolyte, because anyway they said, okay, we have a chiller, or that is some newer technology, they are using chiller, so let's use it. So of course, in tropical climatic conditions, especially at certain times of the year when the temperature goes very high, and if you want, then I think that can be done, but it's not an absolute must. But I have seen people doing it to control the temperature. And many people also stop the formation process when the temperature of 55 degrees or so is exceeded. Is that a good way, or is that not a good way to, ensure that the negatives are also not getting heated up, the battery as such is not getting heated up? And is that not an effective way for the formation process?
That's a good question. I would, thinking about what we have just covered and discussed, over the past few points, I would say it again depends where you make those pauses, where you make those breaks within the formation cycle. So let's think about very early on. The battery is still hot after filling, right? You wait 20 minutes or so, soaking time. Then you turn on the electrical current, and the temperature goes high, right? So you're very early on in the conversion stage of formation. Now you interrupt the formation because you say, "Oh, I'm getting above 55 degrees." So you have a lot of unformed active material or paste sitting there. And what will happen is that if you now stop the current, a lot of sulfation will actually happen in the plate. And then later, when you turn on the current again, you will have to fight this, depending on how long your pause is, large sulfate accumulation, which is an insulator that you will actually find in the plate. However, if we now go again to the last stage of formation, that means the negative is full after about maybe 50, 60% of the entire formation time. If it happens here, there is less of a danger of an interruption causing sulfation or anything, but it will actually help to lower the temperature if the temperature is in fact too high. It's not my preferred method. My preferred method would always be to manage the current just by basically keeping it flowing, but lowering it appropriately. But if you do it in the right phase of formation, I would not be opposed to it.
Yeah, so basically we got to slightly lower the current as we are approaching 55. So once you reach 50, keep a watch and probably lower the current so that even when it reaches 55, it doesn't exceed 55. It will probably remain 55 and lesser than 55, and you can continue charging at a lower rate, right?
Absolutely.
Okay. So far we have discussed mainly the formation of flooded batteries, right?
Right.
We must record another episode to cover the VRLA battery charging. But getting you is difficult. So, and what happens is in VRLA, the charging process gets more complicated with recombination and temperature aspects becoming crucial parameters. So I think we'll do a separate session. And thank you very much, Mr. Achim. I would love to feature you more often in my podcast episodes. The listeners always look forward to my conversation and interaction with you. I get to know this from the analytics, like I've mentioned this to you earlier too. And I'm keen to do many more episodes with you. And I hope you can find some time for this activity, Please allocate some time to me, Mr. Achim. Yes. And thank you, Mr. Achim, for being a part of my episode series again today. And thank you, listeners, for tuning in. Thank you.
Thank you, Ramesh.
Thank you very much.
I owe you at least. I understand I owe you at least one more podcast, but hopefully many more. So absolutely.
No, I am not satisfied with one more. I want many, many more.
Okay. I promise you then.
Okay. Thank you. Thank you very much. Thank you, Mr. Achim.
Please do visit www.rameshnatrajan.in. Keep yourself updated about our new releases by hitting the subscribe button.